So in chapter 1, we talked about weather and climate, and they both deal with the atmosphere, but weather is like short term, and climate is about 30 years worth of average data, condition of the atmosphere. Then the next one, okay, the scientific method, and actually I brought in like a little cartoon of what I did in your notes, the scientific method. You've been exposed to it before. I for sure want you to know between hypothesis and theory. A hypothesis is a working idea. A theory actually is a hypothesis that has been elevated. Okay, and you probably want to know kind of just in general, describe how you go about the scientific method in your own terms. There's a slide in your notes that kind of talk you through it. The next one's relatively straightforward. When we talk about the spheres, the interacting spheres, that is the geosphere, the atmosphere, the biosphere, and the hydrosphere. Relative abundances of gases, I brought in a figure from your textbook. That's this, this one right here, relative abundance of gases. You can't see it very good, but the purple is nitrogen. So most of our gas that you're breathing is nitrogen. It's about 80-20. And the other one is 20% oxygen. The next one, the seasonal swings, year-to-year trends. Seasonal swings and year-to-year trends in carbon dioxide. So again, that figure at the top there, I know it's kind of small, but that is the one that kind of wiggles each year because of plant activity, and it increases long-term. The biggest reason actually carbon dioxide is increasing is because of burning fossil fuels. The next term, where do we get our oxygen from? Plants. The earliest Earth's atmosphere we talked about did not have oxygen in it, and actually we had to develop our water, large bodies of water, and then plants started there and gave us our oxygen. The good ozone layer, hopefully you guys would tell me it's in the stratosphere. Ozone is formula's O3, and what it protects us from is incoming ultraviolet radiation. I didn't say anything in my lecture, but your textbook talks about the UV index, and I think that's kind of interesting. The UV index oftentimes is given as part of your weather forecast, and it's just basically, it's related to, actually, to me, cloud cover. It's like, if it's cloudy, then your UV index is low. If it's clear skies, that sun's going to get you. UV index is pretty high. The next one, we'll be talking more about environmental lapse rate in Chapter 4, but environmental lapse rate actually goes with weather balloons. So environmental lapse rate and weather balloons kind of go together. Basically, environmental lapse rate is how's the temperature cooling as you go up in elevation. Now, we said in the troposphere it gets colder as you go up. In the stratosphere it gets warmer. The mesosphere it gets colder. Okay, in the thermosphere it gets warmer again. So we're going to have that alternating trend. But environmental lapse rate generally is about 6.5 degrees cooler for every kilometer you rise, usually. Then I don't know if you remember this. Okay. But we said with regard to thicknesses, okay, if this layer is the troposphere, okay, actually the troposphere is thickest near the equator. It doesn't really look very good on that figure, but it's thickest near the equator, thinnest near the poles. And to me that kind of makes sense because it's nice and toasty near the equator, a lot of kinetic energy, kind of fluffing it out there. The greenhouse effect, I think I said, actually, it's the wrong chapter, it's a little later, okay, so I say something about it later. But permanent and variable gases, I went ahead and brought, again, they're kind of small, but just to kind of remind you, permanent and variable gases. Permanent gases are right here, nitrogen, oxygen, it's 80-20, and then the next abundant gas is argon. What makes them permanent is that they are kind of constant with regard to amount and constant throughout. Then we have 3 variable gases we talked about. Of course, water vapor is definitely variable. Carbon dioxide's got its own swings, so that's variable, and ozone is also variable. So know those. And then the 4 thermal layers of the atmosphere. So like I said, we have troposphere, stratosphere, mesosphere, and thermosphere. Again, it's really kind of small, but it's just to kind of remind you. And my little notes here in purple is know something about each layer. Hint, hint, okay? All right. Chapter 2. Throughout the course of a day and throughout the course of the year, we kind of have a different, the sun's angle is changing. So we have a couple of interesting phenomena that happen with the changing angle of the sun. Straight up and down is the angle. If the sun were like that, it'd be 90 degrees. If the sun's lower, it's smaller than 90 degrees. So I reminded you what beam spreading and beam depletion look like. Beam spreading happens at an angle, and actually beam depletion also happens at an angle. Bless you. The next one is kind of a subtle thing, circle of illumination. This is my first time to include this as a term. Circle of illumination, the hint I don't know if you can see that orange line right there, the circle of illumination. You see the sun here is kind of coming from the right on that top figure, okay, kind of where the sun's shining. That's your circle of illumination. Okay, think of it that way. And a couple of terms dealing with Earth orbiting the sun, Perihelion and Aphelion. So I brought in this figure from your textbook. Oh, I missed one. I'll come back to it. Perihelion and Aphelion is this one, where actually, again, you can't see it very well, but this is Aphelion over here, July 4th. Aphelion means we're farthest. Okay, perihelion means we're closest, about January 3rd. So going back up one, Earth's tilted axis of rotation, and I don't have it. I think I'm going to add it. If you want to add it, so what is that angle? What do we usually say the angle is? And actually, it's right there. 23.5. It is 23.5. Okay, Earth's tilted axis of rotation. And what that figure does is it kind of marches through the year as Earth orbits the sun and kind of shows you that tilt maintains its direction. Okay, so that actually is the reason for the seasons. Okay, let's see what I put here. Why do we have seasons? Why does our planet experience seasons as we orbit the sun? Because its axis of rotation is tilted. And because its axis of rotation is tilted, we get different angles and varying number of daylight and nighttime hours. So I brought in a table for the next one, solstices and equinoxes. This is something you're probably already kind of familiar with. You know, we're coming up on March, okay? At some point you're going to say, spring is here, March 21st, 22nd, that sort of thing. Okay, that is one of the two equinoxes. So that's the spring equinox. Of course, we have a fall equinox. Then we have the two solstices. So we have the winter solstice in December, and we have the summer solstice in June. And what do they mean? Well, I think probably the biggest thing I'm after there is, for instance, I think there might be a question something about equinoxes are equal. Equinoxes are equal. What does that mean? It means equal nighttime and daytime. Yeah. Probably that's the biggest thing. Kinetic energy versus potential energy. Kinetic energy is associated with motion. Potential energy is what we say stored energy. The next one, latent heat energy. Remember, that was where actually we're like melting an ice cube, or we're taking liquid and we're vaporizing it. Those are two examples where you're putting energy in. Okay, that's latent heat. Then we could go backwards from that. We could go from a gas to a liquid, and actually you're releasing energy to the environment, or a liquid to a solid. Phase changes. Laws of radiation, I kind of stuck down here. Laws of radiation, there's 4 of them. Okay, objects ooze all different types of electromagnetic radiation. The hotter the object is, then it's going to have a bigger curve, which you're actually going to see here in a minute. The hotter it is, also it's going to be kind of skewed toward the short energies. Speaking of electromagnetic radiation, this actually is a figure from your textbook. And then there are 7 cousins, I call them. Okay, so they start out with gamma, X-rays, ultraviolet, visible, infrared, radio, or microwaves and radio waves. So those. Then we talked about the little pan guy, the dude holding the pan, which he probably shouldn't be holding the pan. But anyway, we talked about ways of transferring heat, and there are a lot of them, which is that the fire is radiation. Within the pan is convection and conducting molecule to molecule up the handle. Okay, so know those. And then we get to this cute little curve down here. Of course, the red one is the sun. The blue one is the earth. So you guys would tell me the blue one's squatty, and it's over here to longer wavelengths. Okay, laws of radiation. And last but not least, the greenhouse effect. So remember these things that look kind of like bees right here are actually not bees. These are actually gas particles. Carbon dioxide and water vapor are great at like kind of interacting with the Earth's energy it's oozing off. So that's chapter 2 in a nutshell. Chapter 3, there'll be one problem on the test, and I'm hoping you don't need a calculator, but you guys in your homework did this, where basically the one you're handing for chapter 3, you looked at how do you get an average temperature for the day. Well, one is to add the high and the low and divide by 2. Isotherms, and I brought in a little figure here. It's hard to see, but they have a lot of weather maps have lines on them, and if basically they say those lines are isotherms, then those lines are connecting locations with the same temperature. Isotherms. Yep. The next one kind of goes with it. If somebody says that we have a strong temperature gradient, and I kind of have the red right there on the weather map, basically that means you don't have to walk very far before you get a new temperature. You have drastic temperature changes. Like I said, drastic temperature changes, oftentimes that's when you're going to, we'll talk about what creates wind. I think that is so cool, no pun intended. But so a lot of times if your temperature changes quickly, you're going to have crazy wind, okay, associated with that. Okay, 5 controls of temperature. There they are. Now there's a lot in that one little box up there. So we talked about, for instance, you know, if you're maritime versus continental, that's the first one. The next one is, do you have a warm current or a cold current? Okay, all of those. Altitude is, are you low at sea level or are you up a mountain? Okay, and some of this stuff is really already intuitive. Okay, so be able to pick at least one of those to talk about. How's that? Okay. The next one, specific heat. And I didn't know how to describe it, so I did it this way. So basically, it's a property of matter. And if you want to know what the specific heat of something is, basically you heat it, and however much heat it takes to budge 1 gram of that material up 1 degree Celsius, that's a specific heat. But kind of applying that, we talked about water has a high specific heat. Water has really high specific heat. Soil has a lower specific heat. Something with a high specific heat like water, it means it's really stubborn. Okay. And then kind of back to latent heat. Maybe, yeah. I got it. So it takes energy, kind of, I don't know if you can see this diagram. We have ice cubes, it's solid. We have a liquid beaker full of water, and over here we have water as its vapor. And kind of from left to right, you're adding energy. Okay, and from right back to left again, energy is actually going to be released. And then there's this one. What you're looking at is pole down from left to right. The left one is the northern hemisphere. The right one is the southern hemisphere. And you can see in the southern hemisphere a lot more blue, a lot more. Okay, and actually, when we talk about weather patterns, that the fact that the southern hemisphere has got a lot more water is actually kind of a player in how their predominant weather patterns are down there. But that has an effect on temperature range. And we said that large bodies of water are stubborn, so actually that kind of minimizes their temperature swings. So we talked about that. All right. Ocean currents. And it, again, a lot of stuff in science is like, oh, that makes sense. But sometimes on a test, it's kind of finding your way through what the question is asking. So just take your time. So one of the things you guys would tell me is it's nice and toasty near the equator. It's colder near the poles. And we also talked about ocean gyres that actually go clockwise in the northern hemisphere and they go counterclockwise in the southern hemisphere. We'll talk about why that is. But just if you go ahead, and this is the Atlantic, I go ahead and just make it like that, you can see I'm taking warm up and I'm taking cold down. Okay, warm up, cold down. And that is a good thing because it's not on your test, but we said about 38 degrees latitude, that's where your tipping point is. Otherwise, we have an energy deficit and an energy surplus. So ocean currents are great at that. You guys had a homework question where you told me about cloud cover and its effect on your range, okay, during the day and at night. So kind of maybe revisit that. Lag of maximum temperature, it's just... that's where basically you know the sun, you're going to get your worst sunburn at noon because that's when the sun's rays are most direct, but you're going to feel hottest about 2. Okay, so if you're, which could be a good thing. The lag of maximum, that's what that is. And then we talked about, of course, you guys, when we look at what the temperature is outside, we were all about Fahrenheit, right? Which is English. Metric would be Celsius, and there's another Celsius scale called the Kelvin temperature scale, which is even more awesome. And we talked about, I thought more about, well, maybe they're just fooling us. We can go lower than, and I talked to my husband, he's like, no. So I don't know. So on the Kelvin scale, the reason it works real well is actually 0 Kelvin does mean 0 thermal energy. And then the last one, I don't know exactly what to say. We're all in Iowa kind of familiar with this idea in the wintertime. We have a feels-like temperature called the wind chill temperature, which basically the reason the wind chill temperature is a thing is because it wipes off our our protector, it takes some of our thermal energy downstream. That we wanted that thermal energy. So that's kind of what I'm trying to say. Okay? How we doing? Any questions about all that?